Chapter 4.5, Early Computational Methods. So in this chapter, we're going to be taking a step back to our number system, the one that we're used to, and we're going to be exploring various ways we can do multiplication, the multiplication we know, but in ways that have been used throughout history. So instead of doing long multiplication, right, writing our numbers out over top of each other, carry the ones, etc., instead of doing it that way, there are other ways that multiplication has been done throughout history, and we're going to explore some of those other ways. So, first method we're going to look at is called duplication and mediation. So duplication refers to doubling a number, so like duplicating, duplation. Mediation refers to halving a number. Medium means middle, right? So doubling and halving. This is also known as Russian peasant multiplication, so you can kind of see where it might have come from, but it's very similar to an ancient Egyptian method that's described in the historical Rhind papyrus. We don't need to know the full history of it to really understand how to do it, though. Essentially, what we're going to do is we're going to multiply 25 times 31 using this method. Now, of course, we know how to multiply 25 times 31, right? I can write out my 25 times 31, 1 times 5, 1 times 2, 3 times 5, carry the 1, 3 times 2, I add, I get an answer, etc. I can get that using our method, using the method that we use today. But the goal here is to see what other ways I can do this, right? So we're going to multiply 25 times 31, and the goal isn't to get the numerical answer. The goal is to show how we can get to the numerical answer. So step 1 is we write the two numbers with a dash between them. So 25 dash 31. This is not 25 minus 31, mind you. This is just basically a way to separate the two numbers into two columns. So you may just also write it as columns instead. Either way is fine. So 25, 31. Step 2 is we have the number on the left, drop the remainder, and place the quotient underneath. So 25 halved is 12.5. We ignore the 0.5 and we just write 12. Then double the number on the right and place that underneath. So 31 doubled is 62. So half and double. So times 1/2 times 2. Or divided by 2 times 2, however you want to think about that. And then we repeat this method until the right column displays the number 1. Now, we're not done there, but we're going to go through. So half of 12 is 6, double 62 is 124, half of 6 is 3, double 124 is 248, half of 3 is 1.5, right? Half of 3 is 1.5, but we drop that 0.5 and just write the 1, so just the whole number. And doubled 248 is 496. So now we've dropped down to that 1, so we stop. So what do we do with this? So our next step is to cross out all rows with even numbers in the left column. Okay, so left column being this column, right? So I cross out any whole row that has an even number. So the 12 and the 6 rows both get crossed out. Then we add the remaining numbers in the right column. So we add these. This will actually be our answer. So 31 plus 248 plus 496 is 775, as we saw me find earlier. So why does this work? Well, it's a bit complicated to understand, but essentially what we're doing, because we're doubling and halving, doubling and halving are kind of opposite operations to each other, so they sort of, in essence, cancel each other out. So we can keep doing this, but then we have to keep track of these pieces that we're ignoring because we've dropped 0.5 somewhere in there, and so It's a bit complicated to really understand why this works, but the main thing you want to think about is if I double one number, halve the other, I'm kind of negating myself as I keep going. If you're interested in further understanding this, certainly something you can seek online or ask about for more understanding. But essentially what you need to be able to do is just to do this process. So, while I have this up, I'm going to show another example of it, just to really drive this home. So let's pick any two numbers, right? I'm going to go back to my first 4 steps. So I'm going to pick two numbers. Let's say I wanted to multiply, let's go with, how about 54 times 27. Okay. So, step 1, I have 54. Okay? So, step 1 is I write the two numbers with this dash between them, but after that, step 2, have the 54. So, half of 54 is 27. Oh. That's an interesting coincidence. And then we double the 27. So again, this is not a minus sign, it's just a way to sort of separate columns. So doubling that 27 is going to get me 54. Now I have the 27. Now half of 27 is, let's see, 13.5. But I'm going to drop that 0.5 and I'm going to get 13. Then doubling the 54 is 108. Half of 13 is, again, 6.5, but I'm going to drop that 0.5. So I just put 6. Doubling the 108 gets me 216. Half of 6 is 3. Doubling 216 is 432. Half of 3 is 1.5, but again, we're going to drop that to 1. Double 432, we get 864. Okay, so now, once I have this, my next steps are to cross out all rows with even numbers in the left column. Okay, so the left column specifically. So that's the halving column. So that means I'm going to cross out this row and the top row. Then, step 6 is add the remaining numbers in the right column. So in the right column, we have 54, 108, 432, and 864. So adding all of those numbers together, I'm going to get 1458. So all of this added together is 1458. And then if we go back and check what is 54 times 27 actually on my calculator, it is in fact 1458. So if you're doing this, you want to understand the method, but you also will have a calculator on you so you can check to make sure you're getting it right. Alright, let's look at another method. So the next one is called lattice multiplication. So in fact, this is a method that I learned when I was in elementary school. So it's possible some of you might have heard of this before. It is still used a little bit. I've seen students use it, but if you haven't learned it, that's okay. Maybe you'll start using it now. So the name lattice comes from the use of a grid, also known as a lattice work, which you might have heard of if you're ever into gardening. Those like things that like they have tomato vines growing up are called lattices. It's really just like those grid work, woven sort of with crosses and stuff. Like that's what a lattice is. So we use this grid when multiplying two numbers. It's also referred to as the Galosia method. This method uses a rectangle split into columns and rows, with each newly formed rectangle split in half by a diagonal. So, if I want to multiply, for example, 312 times 75 using the lattice method, my first step is to line up the digits along the top and sides of my lattice. So I already had this box set up for this problem, where I had 3 columns and 2 rows, 3 columns for 3, 1, and 2, 2 rows for 7 and 5. If you're multiplying just 12 times 75, then we just wouldn't have this column. We'd have we'd have a 2 by 2 box. So you just, or if we had times 751, then we'd add another one down here, like so, right? So we just have as many rows and columns as we need to form this box, filling out this pattern. Okay, so I have 3, 1, 2 along the top, 7, 5 along the side. Next, we multiply the number on the top by the number on the side of each box. Then we place the tens digit above the diagonal and the ones digit below. That should say ones, my bad. So, once we do this, for example, I have 3 times 7 is 21. 1 times 7 is 0, 7. We do have to remember to put in our zeros. 2 times 7 is 14. 3 times 5 is 15. 1 times 5 is 0, 5. 2 times 5 is 10. So each of these, we just line them up 1 digit per triangular area. Don't try to squeeze 2 digits into a triangular area. You will get it wrong. The goal is 1 digit. 1 digit between 0 and 9 should go in each triangular area, and there has to be something there. Never leave one blank. Then what we're going to do is we will add diagonals and carry the tens to the next diagonal. So in this case, I have the arrows representing these diagonals. So in this case, we get the first diagonal is just a 0, so we carry it down and we write it down here. The next diagonal is 5 plus 1 plus 4, which is, in fact, 10. So we put a 0 down here and carry the 1 up to the top. Next diagonal, 5 plus 7 plus 1 plus 1. So 5 plus 7 is 12. Plus 1, 13, plus 1, 14. So we put a 4 here, and we carry the 1 again. And then 1 plus 1 plus 1 is 3, and then we just have this 2. So in the end, these outer numbers right here, 2, 3, 4, 0, 0, are the answer to our lattice multiplication problem. So 312 times 75 equals 23,400. So in fact, we can check this using our regular methods, but essentially we're doing a very similar thing to what we do when we do long multiplication. It's just possibly a little bit simpler, though it takes a little bit more effort to write out the method because you have to draw the lattice work. So let's actually, on this blank slide, try out another example and go through the steps. So any numbers we pick once again. So let's go with, I'm going to say, how about 2 3-digit numbers this time? So I'll go with 472 times 531. Okay, so in this case, I'm going to draw a pretty big lattice work. All right, so it's going to need 3 rows and 3 columns because I have 3 digits in each of my numbers. So 4, 7, 2, 5, 3, 1. And then I draw my diagonals. So when I draw this by hand, I usually extend the diagonals outward. It just helps for separating the numbers when you're done, make sure you have enough digits. So the cleaner version I have here where I didn't extend these diagonals, but if I had extended them, we could see that it really shows you like a split off of each of the digits, so it can be helpful. So here we have, we're going to end up with 6 digits in the end. So let's start. So 4 times 5 is 20. So I would put the 2 here, 0 here. 7 times 5 is 35. 1 digit in each triangle. 2 times 5 is 10. 4 times 3 is 12. 7 times 3 is 21. 2 times 3 is 0, 6. Remember, 10's digit, 1's digit. Not 6, 0, it has to be 0, 6. 4 times 1 is 0, 4. 7 times 1 is 0, 7. 2 times 1 is 0, 2. So now we start adding along these diagonals. So this first diagonal right here just has the 2 in it. This will be a 2. Next, 7 plus 6 is 13, which means we're going to carry a 1 into my next diagonal. 4 plus 1 plus 1, plus a whole bunch of zeros, but 4, 1, and 1 are the important ones here. That gives me 6. Then 2 plus 2 is 4, plus 5 is 9, plus 1 more is 10, so I put a 0 down here and carry the 1. Then over here I get 1 plus 3 plus 1, so that's 5. And last diagonal, I just get a 2. So my answer is 2, 5, 0, 6, 3, 2. And now I'm just going to very quickly check this on my calculator to make sure I did everything right. So 472 times 531 is 250632. So that tells me I did the process correctly. So there's a lot of little places where you can do, where you can get a small, calculation error because we're working off of knowing our times tables to be able to do this, right? So you might do the method entirely correctly, but maybe when you multiply 7 times 5, you put 45 instead of 35. And so then you'll be off by a little. So you have to go back and check and make sure you did all of your little multiplications right. Something as simple as that can cause a big error, so it's a very good practice to just go back and check using the technology at your disposal. Our final computation method we're going to look at is called Napier's rods. Now this method is very related to lattice multiplication, but it's actually an early method of computing. So in the early 1600s, John Napier developed a multiplication method which proved to be one of the forerunners of the modern-day computer. So Napier's rods uses a system of separate rods numbered 0 through 9 and an additional rod for an index, numbered vertically 1 through 9. Each rod is divided into 10 blocks. Each block below the first contains a multiple of the number in the first block with a diagonal separating its digits. Units digits are placed to the right of the diagonal, 10's digits to the left. Essentially, just like lattice multiplication, we have these little two triangles, right? The diagonal splitting up a square multiplication table. That's all this is it's an old-fashioned multiplication table. But these are literal rods that people had to do multiplication. So if I wanted to find, just like on a multiplication table, if I wanted to find, let's say, 6 times 4, I'd go to 6, I'd go to 4, and I'd find 6 times 4 right here is 24. So then if I wanted to use Napier's rods to do multiplication, it's going to work very much like that lattice multiplication. But the point is that you would already be provided the rods to work with. So we want to multiply 48 times 365 using Napier's rods. Okay. So step 1 is we're going to break down that multiplication. So 48 times 365, we're going to break down the 48 into 40 plus 8. So in other words, what we really need to do is 40 times 365 and then 8 times 365 and add those together. Now, Napier's rods allows us to do this, where it doesn't allow us to do 48 directly because 48 is not one of the indexes. Or indices, I should say, only go 1 through 9. So now, step 2 is we calculate 4 times 365 on Napier's rods by looking in the 4 row and finding the 3, the 6, and the 5 columns. So we know 4 times 3 is 12, 4 times 5 is 20, 4 times 6 is 24. So now we just do a mini lattice here, and we do the addition just like we did with lattice multiplication. So in this case, we get reordering it so it's 3, 6, and 5 in the proper order. So I get 0 in the first diagonal, 6 in the second diagonal, 4 in the third diagonal, and 1 in the final diagonal. 1460. So once we add up those diagonals, we get 1460. However, we then need to remember that we didn't want 4 times 365. We wanted 40 times 365. So we're just going to add an additional 0 to the end of our number. So 40 times 365 is 14,600. Now we repeat with any remaining indices and then add the results. So in other words, now we need the 8 from 8 times 365. So 8 times 365 equals, we bring out the rods for this. Again, going back to the columns, we look at 8 and we look at the 3, the 6 and the 5, bring those together, and we get our diagonals as 0, 12, carrying the 1, 9, 2, so we get 2920. This case, we actually wanted 8 times 365, so we don't need to tack on any zeros or anything like that. We can just add the result. So it'll be 2920 plus 14,600, and that will be 48 times 365, which is in fact 17,520. Now, the purpose of Napier's rods, again, it's very similar to lattice multiplication. It's really to help with, again, if you have this tool in front of you, you could do this simpler than writing out all of the lattice work. So without the rods themselves, which were basically like an early calculator, people would have these actual rods to do multiplication. If you don't have that in front of you, then the lattice multiplication method is the easier way to just do this, to do it all at once, essentially.